Alright, so last time this is where we were. We just talked about the constructor for a linked binary search tree. So of course we're making a binary search tree. It's going to be a linked implementation, so we're going to use those nodes. But unlike the linearly linked nodes, they have like a left and a right. The constructor for this class is going to be simple. It just has a size and a root. With access to the root node, we have access to everything in the tree, indirectly at least. This is just like the other link structures where we had reference to the head, and that's all we needed to have reference to everything. And the constructor just creates an empty tree, starts nothing in it, it's null, size is 0. Then we've got static node class. I made it an internal class. It's got two constructors, get data, get left, set left, and so on. It's mutable, of course, for better or worse. So then we have add. This is basically where we left off last time, add. So there's the public add, which is just, all it's doing is calling add, but it's calling the private add, the add that takes two arguments, has two parameters. And then this other, the public add increases the size and returns true because that's what the interface says it has to do. But let's go have a look at this recursive add. So this is the recursive one. It's private, and like we've seen multiple times already in the course, it's not uncommon to have a public method that just sets up a recursive one with the corresponding starting arguments for where to start. So we call add. What's the root of the tree we want to start adding on? Well, for a tree in general, it's always going to be the root. So that's why we don't specify with this add, but then it immediately calls the other add, which takes root. So this is a recursive one, and mind the return type. Add returns a node. And this might feel a little weird, but let's talk through this. So it's going to return a node. So if we ever get to the case where the current node is null, like maybe the root is null, the current node is null, if it's null, that's where we want to add the element, right? So imagine this is the root of some tree, could be a subtree, it always is going to be the root of some subtree, and let's say it doesn't exist. So we're going to put the node we want to add right there. So what are we going to do? We're going to create a new node with the corresponding element we want to add. And then we just return that element, which seems a little weird. But let's take a step back and look at the public one. And maybe this will help make the rest of it make sense. When I call add with the element I want to add and the root of the corresponding tree I'm adding it to, I'm reassigning the root to the value that's returned from the recursive one. So again, consider we've got an empty tree. We create a new node in the private. Current is null, because the root is null. Create a new node, and then immediately return it. And then root is now that new node. So this is perfect. But now we need to make it make more sense for the whole recursive thing in general. But of course, we've got to remember, every node is the root of some subtree. So it kind of already is generalized, but let's talk through it. So let's look at not the base case. So if I'm looking at the current and I get the data, and I'm comparing it to the element I want to add, depending on its size, if it's greater than or less than the value in the current, the node I want to add is either going to go to the left or to the right. If it is, what I do is I say, okay, let's say I'm going to the left. Well, I'm going to say, okay, current, I'm going to set your left to be add element current's left. So I'm saying, hey, left, there's the recursive call to add. That's the argument to the set left. I'm calling add, and that add is going to return a new node. And that new node is going to be set to, not necessarily a new node, pardon me, that add is going to return a node. And I'm going to set that node to the current's left. And again, you're going to say like, but hold on, you're saying current.getLeft, and then you're immediately setting its left to what it is. But remember, it might be null. Current's getLeft might be null. And similarly with going to the right. And at the end, we're always returning current. So let's work through an example. Let's say I'm adding the number 2. All right? I jump in with the root. I'm looking here. Is it null? No. Okay. So I go to the left because 2 is less than 10. Current is now, because it's the recursive call, the current is the root's left. It's not null. And we go to the left because 2 is less than 5. So now, in that recursive call, current is the node containing 1. And now 2 actually has to go to the right. So we're going to call add on this node's right child. But this node's right child is null, right? It doesn't exist. It's not there. So suddenly we're at that base case. So we create a new node and put the value in it that we want. I put it in a circle because why not? And then I return a reference to that node. That's what's being returned, is the new node. And then when we take a step out of that recursive call that then finished, we're on a line. In fact, we're on the line where we're doing setRight, right? We're saying current.setRight to the result of saying add the element to the right, on the right child. So this node is now current, right? Because we took that step back out, and we're setting its right to the new node that was returned. Awesome. Then we take another step, and then we return current. But current is now this node. We take a step back. We were going to the left, so now current is 5. And we're setting its left to the thing that was just returned, which was this node. So we just set its left to the node it just was, but that's entirely fine. And then we do that again. This is current. We take it, and that's what's returned. We take a step out. Now current is 10, and we are setting its left to what was just returned, which was the previous current, which was this. And then similarly, we return current, which is the root, which brings us back to the public one, which then just reassigns the root to the root. That's all. It might feel a little strange to always like I'm saying add, like I'm reassigning root. I'm reassigning root's left to the thing it just was. You're right, but we don't know. When I'm looking at 10, and 10 is current, I mean, I could write the code to check if it exists, and that's fine. But based on the code that's there, this code doesn't know if the root's left or right is null or not. It doesn't. So we need to set its left to be the result of adding. Because maybe it's a new node, or maybe we were just going to return the same thing that it was just called on. Either way. Any questions about that? This might feel a little tricky, but if you work through a couple examples on paper, it'll stick. Yes?
Can you scroll up just for a moment so I can look at the public ads?
Yep.
Okay. Just wanted to,
What were you looking for?
I just wanted to like get an idea of what it was. So I can see.
Gotcha. Imagine I've got an empty tree. There's no root. Root is null. If I call add, where the element on root, root is null, we immediately jump into the recursive one. Is current null? Yeah. All right, create a new node with the element we want to add. I don't know, 7. And then we're returning that new node, a reference to that new node. And then back in the public, we're immediately assigning root to the value that was just returned. Well now root's not non-existent. It exists. Great. But that's what's happening at every call. It's just that this is the root of the whole tree, but as soon as we find the root of a subtree that doesn't exist, you create it. That's just what we just did here. But of course, this is recursive, and it goes down until it finds the right spot. Now notice that this add is just like a binary search. But the difference is, if we ever find, like with a binary search, as soon as we find the element we're looking for, we stop. Here, well, we keep going until we find an empty spot, and then we put it where it belongs. And this is why, let me ask you this. What is the computational complexity of an add, assuming you've got a reasonably balanced tree? Log n, exactly. Because the furthest it's ever going to have to travel is the full height of the tree. And we know the relationship between the number of nodes in a binary tree and the height of a binary tree is that like log base 2n. Like if I'm adding the number 8 to this tree, there's only one spot it could go. It has to go here, given the state of this tree. If I'm adding the number 11, it has to go here. It has to. And it's as far down as that we can go. The worst case scenario would be like going and adding to the 2. I want to add 3. Well, the 3's got to go to the right of 2. Any questions about that add? Yes.
I'm a little confused on how it gets down to the null and then it puts it there. How does it backtrack?
How does it backtrack? Well, that's just the recursiveness of it, right? So consider I'm at some arbitrary step. Like let's say I'm adding the 2. All right? Right now, so on the first call, I'll add like a 1 here. The current was the root. Then on the second call to the recursive function, 5 was the root, or current. The third, that's the 1, and this is where we're currently at. And we're saying, okay, I want to add the number 2, and it's got to go to the right. So I'm currently on line 37. Okay? So I'll put a 37 here. And on this one, I would have been on line 35. And this one would have been a 35 as well, because we're going to the left. And then on line 37, we're going to the right. Line 37 says, okay, current, I'm going to set your right to the result of that method, of that recursive method call. So we're going to hit pause right there. So now we got to jump into the third recursive call, or the fourth. That's pointing to a node that doesn't exist yet. That's to the right of 1. Current is null right now. Do you agree? So that means we're at the base case. So what am I going to do? Well, I'm going to make a new node containing the element. I'm adding the number 2. My marker's starting to go, but hopefully you can see reasonably well at the back. I'm adding the number 2. And then I immediately return that node. Right? I'm returning the new node that was just created. And when that happens, it's a reference to that node. It looks like you just went, oh, yeah, perfect. But let's work through this anyways. So we're returning a reference to this node. So I now have a reference to that node. We jump, and then whenever we hit the return, that recursive call ends. So we're done here. And when I get back to line 37, I have a reference to this node. And what am I doing? Well, on line 37, I am finishing the line 37, which is current set your right to that new node. Boom. Now it's actually set. Then we're done. We go to line 39. We return current. Current right now is this node. We're finished that recursive call. We're on line 35, which was calling add on the left, which was this. And from that, I just got a reference to current, which was the node containing 1. And I'm immediately setting the current, which is currently 5, the node containing 5. And its left is being set to what it was just called on, what was just returned, which was a reference to this node. And then we return current. So, like the between method calls, right? So this is current that just got returned on line 39. So I have a reference variable to this 5. I'm now on line 35 of the first method call where current was 10. And it just finished calling add on its left. And it got back a reference to the node containing 5. So, current set left to the node containing 5. All right, it didn't change. It got set to what it was before. And then, that's done. We return current. Current is 10. So when we return back to the public method, root equals what was just returned, which was a reference to the root of the whole tree. Hopefully that was even clear that time. A little bit more details that time around. All right. All right, minimum and maximum. Now, I wrote these in 2 different ways. One recursive, one iterative. I could have done them both recursive, could have done them both iterative, I could have done them in the other order. It doesn't matter. I'm just doing it 2 different ways for the sake of showing you. So if I want to find the minimum or the maximum value, well, remember, minimum is always the leftmost node in the tree, in the whole tree. And maximum is the rightmost node. So in this particular example, 1 is the leftmost node, so it must be the smallest number. Because if it wasn't the smallest number, it must be to the left of 1. But because nothing is to the left of 1, it doesn't exist. Now, if you're ever worried, like let's say that wasn't a 2, let's say we had a 3, and then a 2. If you're ever wondering, well, hold on, how come this is the leftmost and that's not the leftmost? But remember, that 2 is ultimately to the right of the 1. Even though you're like, oh, well, it's still in the right subtree. Everything in the right subtree of 1 must be bigger than 1 by property of the binary search tree. So min. So here's a recursive min. So first we've got the public facing one. If it's empty, this assumes we've got an is empty written. It's just going to be like a size 0. If it is empty, we're going to throw an exception. Otherwise, return the result of calling min on the whole tree, the root. And then if we go look at the min, the recursive one, the private one, it takes a node. And what we do is we say, okay, current, is your left null? Now, we know current exists the first time it's called. Why do I know that? It's not a trick question at all. I just want to know if you know why I know. Current must exist the first time the recursive min gets called. Because the tree's not empty. Is that what you were going to say? Because the tree's not empty. Why do we know that? Well, because if it was, we would have thrown an exception. So the tree isn't empty, meaning the root must at least exist. So I say, hey current, is your left null? If it is, I can conclude there is nothing to the left of that tree. Meaning that the node I'm currently looking at, the current node, must be the smallest element in that tree. Because it is possible for the root to have nothing in the left subtree. If the current's left isn't null, meaning there's something there, well then return the result of calling min on the current's left. So it's like, look, we asked 10, hey, is your left null? No, it exists. All right, call min on this. So now I say, hey, current, is your left null? No. All right, call min on this. Hey, current, is your left null? Yes. Okay, great. Return current's data, the 1. And then the previous one, I'm returning the result of the min. Take a step out of the recursive call, return the result of the min, return the result of the min until we get up to the top. The result is 1. So that's the recursive min. Here is an iterative max. We could have made an iterative minimum as well. You just flip the directions. But here's an iterative max. If it's empty, throw an exception. Otherwise, hey, if the root's right is null, return the root's data. Otherwise, get the right, call it current. Well, current.getRight is not null. Current equals current.getRight. What does that say? First, okay, let's take a step back. I don't really care what's to the left of 7. But this tree is not null. And I say, okay, hey, root, is your right? Now, mind you, this is root that I'm asking, not a current or anything. It's root. Root is the class's field. I ask, hey, root, is your right null? If it is, I can stop, because that means the root is the maximum. Otherwise, I create another temporary variable called current, have it reference that one, and I say, actually it looks like I started off at root's right. Let's 10. And then I say, okay, well current's right is not null. 11, whatever. Well, current's right isn't null. Current equals current's get right. This is like iterating over a linked structure. Current equals current.get next in a loop, right? But the difference here is I've got 2 choices, left and right. But because I'm looking for the max, I don't care about the left. I'm always going to go to the right. So this is just like a linear search, but just down the right side. That's all this is. But I could make this recursive. There's nothing stopping me. The only reason I have one recursive, one iterative is the sake of demonstrating. Any questions about those 2 methods? Now be aware, these are returning the data. Just like if you're wondering, why are you returning the data and not the node? Well, remember, with a stack or a queue, I don't want to return the node, or bag. I don't want to return the node, I want to return the element that was at the top of the step. I don't care if it was in an array, I don't care if it was in a link structure, I just want that top element. Same idea here. I just want the minimum element from the tree. Don't give me a node that I got to get the element out of. No, just give me the minimum element. Now, remove min and remove max. Remember how we were talking about these, how they could be a little tricky, right? Now, I'm not talking about the general remove. The general remove was extra tricky. The remove min, remove max, if the element I'm removing happens to be a leaf node, like if I remove 12 from here, whatever, I can remove it. But if I remove 1, I might have an issue, because it's an internal node. Or if I remove 10, I might have an issue. It's an internal note, but obviously I wouldn't remove 10 in this particular example because 10 can't possibly be the minimum or the maximum because it has a left and right child. But if I remove 1, I've got a bit of an issue. So finding the minimum and maximum is easy, but removing from the tree adds extra complexity as it needs to preserve the binary search tree property. So remove min. There's a public and a private one. It's going to be recursive. So remove min. The public one has a return element starting at null. If it's empty, throw an exception. If the root's left is null, then I'm going to return, the return element is going to be the data in the root. This is just checking, hey, does the root happen to be the minimum value? If it is, okay, that's fine. We just got to get the data out of it. But then we've got a problem. That would be like, I've got a tree that looks like this, right? I want to remove 7. How am I going to do it? Well, what does the code say? Well, I just update the class's field of root to be the root's right. If root is the minimum, I could very safely just say, okay, now this is the root. The root's right value is the root. It's also possible that the root's right value is null, but that would be fine too. If the root's right value is null, well then we just made the tree empty, which is fine. That would be the case of if the element, like the 7, was the only element in the tree. It's both the minimum and the maximum, but it's fine. So if it's empty, we're going to throw an exception. If it's the root, well, just update the root of the whole tree to be the root's right subtree. And then there's the more general remove, which is return, which is remove min. But we call remove min on the root and the root left. But what are those two arguments? Well, we've got parent and current. See if either of these work. So let's say I'm trying to remove 1. All right? So I'm going to go, okay, I asked it on the 10. It's not empty, and its left exists, so we call it on this. Not empty, and its left exists, so we call it on this. So now we are here. Current's get left is null. All right, that's dead. This isn't too bad. Current is the 1. But you'll notice that this method has an argument, has a parameter parent. And the parent will always just conveniently be the parent node. Because look at the first time, let's say I'm calling it on root. Let's just make sure this makes sense. I'm calling it on root. So I want to go to the root's left. So I'm looking at, let's go to the public one. I'm at root. I'm at 10. And I say, okay, there's something to the left of me, so I got to go down that way. So when I call the private recursive remove min, I give it a reference to the root, which is this node, and a reference to the root's left. And if you look at the private one, well, the first parameter is the parent reference, and the second parameter is the current. So when we get down here, we're in this situation. We have a reference to this node's parent, and we have a reference to, well, the current node. So what are we going to do? So its left is null. So I can say, parent, set your left to current's right. So that then goes, right? which is going to preserve the property. Because all that, look, we can conclude current has no left. Because we just checked, because current's being removed, there's no smaller element. So there's no left subtree that's going to be marooned here. The only thing that could happen is it has a right subtree. It could only have a right subtree. The current node's right subtree, every value in current's right subtree must be less than the parent. Because it's down the parent's left subtree, it must be less than. So by just saying, hey, okay, that's your left subtree now, nothing was lost over here. Everything over here is going to be left alone. The only thing changed is that this points to this now, which is fine because all these values must be less than 5 because it was to the left of 5 already. So it's fine, it's safe. Nothing gets lost, everything is preserved, no properties are lost, it's fantastic. And then when we're done, we return the, we return the data from current, all the way back up because it's recursive. It's possible that if this is a leaf node, right? If this is a leaf node, there is no right subtree. But that's the same as before. If there's no right subtree, when I say, hey, parent, set your left to this one's right subtree, and this is null, well, that's fine. 5's left subtree now references null. It's an empty subtree. There's nothing to the left. It's fine. Nothing is lost. It's all okay. It just gets, this parent set left gets set to null. Great. It should be. There's nothing there. We're happy. Any questions about that? I want to make sure I'm not going too quick on this stuff because I know it can be a lot to kind of wrap your head around. But if you do find yourself struggling, just go take your time, work through it, make sure everything's there. Grab a sheet of paper and a pencil. I know I've been saying it in labs, but if it wasn't obvious to you before, it's probably more obvious to you now. We're dealing with trees. You're going to have a really hard time keeping track of all this in your head. When you have it on a piece of paper and a pencil in front of you and you draw it out, you're not going to lose track of anything. It's going to help you wrap your head around everything so much better. I think I said it before, one of the best investments I made during undergrad was I bought myself a little whiteboard like this. I saved a lot of paper because I was just drawing a lot of trees. It was on a tree assignment that I bought it where I'm just like, F this. So I recommend it. So above are two functions that work together to remove the minimum value. Really it should say methods, but whatever. First, take note of the public method. It checks if the tree is empty. It checks if the root happens to be the leftmost node. Great. If the public method doesn't remove the minimum, the recursive private method is the one that goes for. Okay, at this point current exists. It's not null. Yeah, whatever. We just explained it. Now here is a remove max, but like the max, I made an iterative version. It could be recursive. There's nothing stopping me from making it recursive. But I did it iterative for demonstration purposes. So what does it say? Well, we start with a return element null. Is empty, throw an exception. If the root's right is null, we're done. The root's right, if the root's right is null, we've got the maximum value. The root has the maximum value, and if that's the case, we get the data from it, and we set the root to now be the root's left, because we want to remove the root because it has the maximum value. Right? Yes?
Just reminding you that you said you have to leave early.
Yeah, I know, I keep looking at it. Yeah, I know, we'll probably get this and then we'll wrap it up, but thanks for the things. So if the root's right is not null, we've got a tree that looks like this, and I still need to go find, I gotta go find the rightmost node. So what do? Well, I create a parent reference variable. It starts at root because, well, the parent node would be the root the first time through. And the current will be root's right. So we would have a situation like this, where this is C, and this is P. And all we're doing is like the same idea as the find max. But this time, we're going to iterate down the right subtree, but with both of these reference variables. You know? Actually, it's probably going to be more like this. But it's not going to matter. Because what does it say? Well, current's right isn't null. Let's pretend it's not null for the sake of argument. There's something here. Parent is current is current's right. See, it's just the iterating over a link structure, but here we've got a left and right, but we're always going for the max, so it's always going to be go to the right. So it's just move them down until current's right doesn't exist. As soon as current's right doesn't exist, we know we've got the maximum value, and if that happens, well, the parent's right is going to be this node's left. It's just the inverse, it's just the mirror of the remove min. Again, there's nothing to the right of current, because if there was, it wouldn't be the maximum. The only thing that could exist is this one's left subtree. In this particular example, it doesn't exist, which is fine. But if it did exist, we just promote this up here, because again, nothing's marooned over here, because nothing can exist. And anything here is already a binary search tree. And it must contain values all greater than 10, so it's safe to just promote it up. That's all we're doing. That's it. So that's the remove min and remove max. It's probably kind of obvious to you. To me, I find this particular method here, it's an iterative one. I find this particular method makes it pretty obvious the similarity of the ultimate underlying algorithm, the similarity between the iterative and the recursive. We used a while loop to do the updating the current in the next. The recursive didn't use a while loop, it just made another method call, but the parameters changed. The arguments that were given were updated to be the current's next and the parent's next. And it's the same thing. We've got a reference to the parent and the current, and we're just updating them accordingly once we find what we want to remove. To me, this is a nice example because it makes it really obvious the comparison between the recursive and the iterative and how it's the same algorithm. It's just one used a while loop, the other one used recursive calls. Cool. We'll wrap up.